Hello and welcome back to the Nexperia Power Live Industrial channel. We're live again and continuing our discussions this morning on how to parallel multiple MOSFETs using optimized current sharing technology. As previously, the session will be scheduled for approximately 25 minutes. We'll run a short presentation and then open the floor to questions. Contributions are still anonymous. Ask any questions to our experts, but also please feel free to share your own knowledge and experiences. Questions can be asked throughout the session using the orange speech bubble in the bottom right-hand side of your screen. We're joined again by Stephen Waterhouse, Product Manager of our Power MOSFETs division, who is now joined by Stein Nesbach, Applications Engineer. And with that, I'll hand over to Stephen to begin.
Hi. So this session is on parallel use of multiple MOSFETs. So usually when MOSFETs are connected in parallel, you want them to share current. So the type of markets and products where this is applicable, you can see there the MOSFET voltage is normally in the range of 40 to 100 volts. And again, power up to 10 kilowatts. So if you imagine a forklift truck, with a 10 kilowatt drive on it, it's got to move some very heavy material, and this may require maybe 100, 200 MOSFETs to drive that motor, and a lot of those MOSFETs are connected in parallel. These are switching applications, so it's not a DC. We don't just turn the MOSFET on and leave it on. So these are switching applications, and we want the MOSFET to share current equally during that switching cycle to avoid any imbalance. Okay, normally engineers would consider plus or minus 10 volts threshold voltage range to be sufficient to achieve equal current sharing. A typical sort of threshold voltage is normally stated on a data sheet at 1 milliamps based on a junction temperature of 25 degrees C. So even if we did have a very tight limit on that threshold voltage, the 1 milliamp and 25 degrees C isn't really what we'd see in the application. Okay, the solution we've adopted, it doesn't require to match that threshold voltage. So even though we call it match VT, that is the market that we're addressing. So we don't need to match that threshold voltage to achieve the balanced dynamic current sharing. Normally we've matched VT because it has special screening and sorting in manufacturing. That adds cost and complexity. Nexperia's solution does not. We do it from a design point of view. We design this capability. The current sharing technology ensures a MOSFET will share current more equally during switching, even in non-ideal conditions. So this is during the turn on and turn off of the MOSFET. And it's a passive solution. We don't require any special drivers or any control or feedback. This is a purely passive solution. The MOSFET will share current based on the technology that we've designed. I'm now going to hand over to Stein, who's going to go into a little bit more detail about what we've done and some of the testing we've done.
Thank you, Stephen. Now we need a way to test the new current sharing technology. So here we have a simplified diagram of what we've implemented, where we have a half bridge with 4 MOSFETs in parallel on the low side, as we can see. And each MOSFET is connected to a current sensor. This way, we know how much current is going through each MOSFET at any given point in time. Now, top right there, we're driving an inductive load at 20 kilohertz as a standard frequency throughout this entire test. Next slide, please. So for us to compare the technologies, we have 2 boards here using the simplified diagram as we just discussed, where we have regular MOSFET technology versus the current sharing technology. Now we have 3 devices with the same threshold voltage selected from the regular MOSFET technology, placed where the arrows are showing. And we have the current sharing technology. We have 3 devices with the same threshold voltage again, placed where the arrows were showing before. Yeah, like that. And then we selected 1 device from each technology, which has a 0.5 volt lower threshold voltage. It's marked with a triangle there, so it's device 18 for regular MOSFET technology and device 10 for current sharing technology. With a 0.5 volt lower threshold voltage means that 1 device in both setups will turn on earlier. Now keep in mind, both these setups are identical. It's the same load, it's the same switching frequency and the same bus voltage. The only difference is the MOSFET technology used on both setups. Next slide. Now here we see the comparison where the top graph shows the regular MOSFET technology against the bottom graph, which is the current sharing technology. And these are current waveforms. Now keep in mind, the blue line on the top and the green line on the bottom are the devices with the 0.5 volt lower threshold voltage. And as the red arrows here show, or red circles show, we're interested in the dynamic regions here. That's what we're targeting with this technology. Now, as we can see, there is a big difference in peaks with the regular MOSFET technology compared to the current sharing technology. But also keep in mind that the amount of time they're not sharing current is considerably longer. So for the regular MOSFET technology on the top, it takes roughly 10 microseconds until they start sharing current equally, compared to the current sharing technology on the bottom, where it takes right under 4 microseconds and they start sharing current more equally. Now keep in mind, if a device is turning on earlier, that also means it's going to turn off later. And if we look at the turn off waveform here, we can see that the turn off spikes are considerably worse for regular MOSFET technology versus the current sharing technology, which is what we've also been trying to fix. Next slide, please. And we can do another test, which is to test the current sharing performance at temperature. And the purpose of this is to demonstrate the stability at mismatched temperatures. And what does this mean? So if we have a PCB, like we have two PCBs right there, if there is a difference in temperature across that PCB, how will that affect the current sharing capability of the two different technologies? So the way we did this, we heated the devices as the arrows show, and we heated them at the same rate at the same temperature. So again, it's an apples to apples comparison, keeping everything equal here. The only difference is the technology again. We have 3 captures, one with no heat. Test 2 has heat applied for 2 seconds, and test 3 has heat applied for 4 to 5 seconds. And if we look at the results, next slide, please. We can see here, this is the graph we just saw 2 slides ago, where the top left, it's a cold test. Now, if you click one time, yeah. Now we've made a mark of the current peaks at cold. And as we can see, the current sharing technology is already performing better. However, if we now click one more time, we can now see that the current sharing technology is staying dead on stable on the bottom there, compared to the top side where we have the regular MOSFET technology. And if we click one more time, we can see that they start slipping apart even further. So the regular MOSFET technology is now slipping apart as it's heating it up. Now the current sharing technology, because it doesn't rely on matched threshold voltages at the beginning, this heating effect doesn't affect it. Now this also affects the turn off portion of the waveform. Now you might wonder, Stephen, can you go back one, please? So you might wonder why it's like that, yeah. You might wonder why it's actually changing as it's heated up. And that's because threshold voltage has a negative temperature coefficient. So that means as temperature increases, the threshold voltage reduces. So it's turning on even earlier. So remember the blue and the green lines here, they're turning on earlier. Now, another very interesting point is that these dynamic responses that you see here, they're always fixed regardless of frequency and duty cycle. So these spikes, if you were to increase frequency, they wouldn't change. What would change is the steady state region at the end there, and they would come closer together. Now we have a demo video showing this effect on screen, so it's a bit easier to follow. So please have a look at that one as well. Next slide, please. So as a conclusion here, we can see that the temperature differences in the PCB mean that screened threshold devices no longer maintain the matched threshold voltage. So remember, as the temperature goes up, the threshold voltage goes down, so it changes at temperature. Now, the Nexperia current sharing technology does not rely on matching threshold voltages, so it's tolerant to these differences in PCB temperature. Now, also, the Nexperia current sharing technology is optimized to share dynamic current more equally, and it doesn't rely on the matched threshold voltage, so you don't run the risk of, if you have uneven temperature across the PCB, that it will affect the current sharing capability of the different MOSFETs. Next slide, please. And with this, I hope this information gave some understanding on how we are approaching the problem of achieving equal current sharing between MOSFETs in power layering applications. Please feel free to share any questions you have or any insights you have on paralleling applications. I'll have to put them up.
Thank you, Stein and Stephen. Okay, let's open the floor for questions. Just to remind everybody, if you want to ask any questions or share any of your own insights, you can do so by using the orange speech bubble in the bottom right of the screen. We do have a couple of questions in, so let's start with, do you have PCB layout recommendations for high current applications?
Shall I take that one, Steve?
Yeah, you take that one, Stein.
Yeah, so in this study, we did some studies on layout and the way we assure that the MOSFETs would share current relatively equally. In terms of layout recommendations, we're not a board house, we specialize in MOSFETs. I believe we will be releasing an application note on the solution we have found to be working well. But I would like to highlight that we're not a PCB house and we do specialize in MOSFETs. But yes, we do have some insights in how to do the best paralleling layout from our perspective again, and that will be released in an application note sooner.
Thanks, Stein. Next question, why is this technology better than screened devices?
Shall I take that one again, or?
I can start. So yep. We'll do this between us then. So the problem with screening devices is you are screening out a lot of your production devices. So even for example, we need to make 10 million devices to screen out 1 million devices. The cost of those unused 9 million devices is going to be added to the cost of the screen devices. So it makes it's not a realistic thing to do. We know some manufacturers will screen out devices, but usually these come at higher cost. So we wanted to avoid that. We didn't want to be left with devices which was outside of our normal distribution to throw in the bin at the cost of production. And I'm sure Stein has some technical reason why we wouldn't do that as well.
Yeah, so just to build on what Stephen said, keep in mind that by screen devices, you're screening them into certain bins, and then those screen devices has to follow through the entire production line all the way until the end application. So you have to make sure that the correct screen devices are following through together through the entire application manufacturing steps. Now, also, as we saw at temperature, so if there is a varying temperature across the PCB, the matching threshold voltage devices that you might be getting, they're not going to behave to the same level as you were expecting at 25 degrees. So if you've got one side of the board running hotter than the other side of the board, for whatever reason, the threshold voltages, they will start to slip apart, as we saw. And that's also something worth taking into consideration. And there's also the entire cost aspect of screening devices specifically, where with the current sharing technology, we intend to have this at a larger manufacturing scale.
Thanks, Stein. Okay, next question. What is the technology used in the current sharing, and will it work when devices have different series inductances in drain source terminal?
So in terms of the technology, obviously this is intellectual property. We believe we're the only manufacturer who's developed this type of technology. And it's confidential, but we can't share company secrets. In terms of the different inductances in line with that, again, that's usually down to your PCB layout. And I would say we tend to be tolerant in terms of temperature, but maybe Stein has considered differences in that as well, whether we've got inductance in the path.
Yeah, I'm not entirely sure I understand the question about inductances. If it is in terms of PCB inductance, that should be fine in terms of sharing. If it's in terms of adding an inductor to each MOSFET, that's a bit of a different question, and that would require us to do a bit more analysis in that regard. Yeah.
Okay, I'll move swiftly on. We've got a lot of questions coming in. Can you please explain again, how is this current sharing technology different to matched VT transistors?
Okay, so I can take that one. I can explain it a bit better. So if you're trying to screen devices for similar threshold voltages, so you have, for example, 10 devices, and they have a difference in threshold voltages, all of them. So that's within the regular distribution. Now, the regular way to do this would be to select a specific few devices with similar threshold voltages, and then take these devices and put them on a board, and then they would run relatively similar together. That does include some problems that we highlighted with temperature and differences in temperature, but the current sharing technology doesn't have to do that screening. It doesn't need to have 10 devices and then select 2 and then with the same threshold voltage. It doesn't rely on similar threshold voltages to share current equally, right? So that's the point. So we can still have that full 10 device with different threshold voltages, and it would still share current together. I don't know, Stephen, do you have anything to add to that?
Yeah, so the two technologies are completely different. So sorting and screening uses what you're basically doing is sorting and screening standard technology. The Nexperia solution is an optimized technology, so we can't really compare we compare the two in the application and say how they perform against each other, but the two, you're using a standard technology with something that's optimized. So we know how to solve some of the dynamic issues, so during the turn on and turn off of the MOSFETs in parallel, and that's what we've targeted. So we do this by design rather than having a standard design and then trying to have as tight a production capability as possible, which comes at cost, and then having a screen and sort solution, which adds even further cost. And again, you'll remember that when Stein tested these devices, he tested devices on both tests with a standard and the optimized test with a 0.5 volt difference. That 0.5 volt difference, so that one device which was a different threshold voltage, that represents a plus or minus 8% window for your threshold voltage. And as I mentioned, most of our customers would consider plus or minus 10% as an adequate screen. So even with what our customers consider an adequate enough of a screen, an adequate screen, you still get this difference in dynamic performance. And that's why we developed this technology. It's because we know that screening the devices, you need to get them as close as possible. So you need that very, very tight tolerance on the MOSFET, which is representing maybe 10% of your product distribution. So 90% of what you produce needs to be used elsewhere. When you're manufacturing these devices, we don't want to be manufacturing 10 million devices and taking 1 million devices for a confirmed order, because now we've got 9 million devices on the shelf that we've not got a customer for. So this is one of the reasons. There's commercial reasons and technical reasons why we wouldn't do the screen and sort. But yeah, the two solutions are completely different. One is optimized for a particular application, which is what the current share device is, and the other one is just standard production.
Okay, thanks, Stephen. Next question, are there any steps taken to reduce the steady state current sharing mismatch with temperature, not the transients only?
You want to take that or shall I take that?
I can start with that. So usually by steady state, we're talking about the conduction losses. So we focused on the dynamic. The steady state is due to your conduction losses. And as you'll recall, we had a 0.5 volt difference in threshold voltage, which means even with our optimized solution, so we try to get the dynamics matched, there's still going to be a RDS on difference because of a different threshold voltage. And these conduction losses, normally they would reach equilibrium in a circuit. So the longer you leave it in conduction mode, it will equal out as a normal sort of benchmark. So no, we've not considered the conduction mode, but we don't see that as the biggest power losses. That would normally be self-writing.
Yeah, well, I can add to that as well. So remember about the temperature coefficients that I mentioned. So threshold voltage, if it gets heated up, it starts changing. Now with the resistance, as temperature is applied, the resistance starts increasing. So if one device is taking more current, its resistance is going to increase for conduction losses, and it will start drawing less current. So it's a bit of a self-balancing effect. The reason why you maybe saw that where we applied the heat and you saw them shifting apart, the reason why you saw that is because we're applying external heat to the devices. So it's not the device is naturally heating up and controlling itself. It's rather we are forcing the device to be hot. Now with dynamics, the problem there is as the devices start getting a bit different in temperature, it actually gets worse because again, the threshold voltages, they start shifting away from each other, which is a bad thing. There is no self-balancing. And also keep in mind that when you're switching, you're going through the linear region and you want to stay there for a relatively short period of time. So if you have a very large current spike going through one device and you have a large voltage across it because you're in linear region, that from our perspective, that is considerably worse. And that's why we focused on that for now at least.
Thank you, Stein. Okay, I'm going to group a couple of questions together here because we're getting a few of the same. How do you identify from the MOSFET part numbers which have current sharing technology? And are these a separate family of MOSFETs or are they with the general MOSFET family?
I can answer that one, Stein.
Yeah, take that one.
Yeah. So yes, we will have a different suffix for this. I think it's J. So the last letter in the part number would be J. And once we're currently using our 100 volt platform to test this technology and to optimize and to make all of the optimizations. However, whatever we do with this 100 volt platform, we can apply to other platforms as well. So it's a technology that we can apply to most of our MOSFETs. So if you have a 30 volt device and you have a specific requirement to share current at 30 volts, in the future, we will be doing current sharing devices at every voltage level we release. We see this as a big market. For some of our manufacturers who use 200 MOSFETs per motor drive, if we can reduce that MOSFET count to 100 or 150, because they're now sure that they're sharing current more equally, then there's a big benefit to our customers. But yeah, its suffix will be J, and it's something we can apply to any of our MOSFET technology.
Anything to add to that, Stein, before we move on?
No, not really.
No, okay. Okay. Okay, we've actually run out of time for questions. We have had an awful lot of questions in. So what we will do, because we didn't manage to answer them all, we'll group those together. We'll get Stephen and Stein and some people from the power team to provide some answers to those, and we will publish them online after the event as well. So thank you again, Stephen and Stein. Again, you can take a look below the video screen where you can find further links for information on our power MOSFETs. But quite importantly for this technology, it is a new technology. It's not released yet, and we are looking for people to volunteer and test this in their own designs. So if you're interested, there is a form that you can complete under this video screen as well. I think Stein already mentioned, but it's worth mentioning again. You can actually see these MOSFETs in action on the on-demand section of this industrial channel as well. So with that, thank you very much for your time. If you do have some more time, please do stick around. We'll have our final live session on the industrial channel in about 5 minutes with our special guest Instagrid, so we can hear more about their innovation for the world's most advanced portable power supply. Thank you.